All right, physics, in continuation of our discussion of SI units in the last video, right now we're just going to talk a little bit about the applications of SI units to help understand why we need to use them. Why does everything need to be in meters? Why does everything need to be in kilograms? Well, number one, confidence in the interactions between us and nature. We got Neil deGrasse Tyson here trying to repeat somebody's experiment that somebody else devised in the world hundreds of years ago. And if we didn't have a common way of describing the units of measurements and formulas, Neil deGrasse Tyson might hit himself in the face. Okay, so it's important that we have a common understanding of units for measurement so that we can repeat other people's observations. And more importantly, we can also manufacture technologies internationally. Somebody that is designing a car in Germany, we can manufacture it in Ghana. For example, Ghana is making Volkswagen now, and we can do it just as precisely as German technology here in Ghana because we're all going to use SI units, and we can create everything that'll fit perfectly because we're on the same wavelength. Another thing that we can do is have more people working on the same problem if we're speaking the same language. And this is more kind of a nature of science thing that we need to learn in physics and in your TOK classes. This results in collaboration, and we seem to be advancing as humans much quicker if we collaborate and share information and have more people working on smaller pieces of the problem. In order for us to do that, we have to have the common language. All right, and for me as a human being, even without thinking about big problems, I want to make sure my car works perfectly. So I need to know exactly how much air I need to put in the tires, what pressure it should be, how much fuel goes in the car. And even this is a battle today. Many accidents happen because people are not using the same units of measurement, and they pump in the wrong amount because they didn't do their unit conversions properly. So cars and the problems in fixing cars and airplanes still happen today because we're not on the same page. So this is all stuff. You'll notice in my classes I talk a lot about this, but in DP you need this stuff to talk about TOK links, to create an essay in TOK, and also in the IB exam you have to mention this kind of stuff. What is the importance of SI units? You'll notice in your textbook you have a lot of these discussions as well, and you need to take note of that because it does appear in multiple places in your IB course. Okay, so SI units, as presented in the last video, are our fundamental observations of the universe. If I look at the universe around me, these are the fundamental things that I can see. Those are the most basic measurements I can make of the universe around me. Everything else, I'm sure we have lots of other measurements. I mean, for example, we all knew from last year, force is measured in newtons. I don't see newtons anywhere on that wheel. Hertz is frequency. Pascals is how we measured pressure last year. Joules was work or heat energy. Watts is power. All those were units we used last year, but they're not on this wheel. Well, that's because these units are created from combinations of those fundamental units. So when we look at the universe through these units, we see relationships between them, and those relationships allow us to calculate more interesting units called derived units. So the combinations of these units create derived units, and the relationships between them are new units that are usually named after the person who discovered it. Like Newton is for, I'm just going to change the color here, for force. Okay, Pascal is for pressure. Okay, Hertz is for frequency. Why am I writing this down when it's written over here? Okay, Joule is energy. Okay, work, not really. Yeah, energy and work, yeah. Heat, that's definitely really. And watt is the rate at which we use energy. Okay, joules per second. So those are all derived units. A derived unit is any unit that is a combination of all the fundamental units. Okay, you can see here, even though that's a fundamental unit, we've done some math to it. 1 divided by it. So that's a derived unit, kilograms, meters, second. Okay, so sometimes in your textbook, you're going to see that a unit that you know for force, which is newtons, is actually written in this form, where we have the base units, the fundamental units expressed. Okay, force, a newton, is equal to a kilogram meter per second squared. Okay, so here's just an example of a table that you would have in your textbook for the units, derived units, and the common symbols for those derived units. But you need to know that those derived units come from the fundamental units and the combination thereof. All right, so let's just practice. Show that velocity is a derived unit. Okay, so here are the fundamental units. Okay, and velocity is a derived unit if it's a combination of those fundamental units. So we know from last year that velocity, velocity is the rate of my change in displacement, that's displacement, if you remember the symbol for it from last year, over time, okay? Displacement is measured in meters, so it's going to be equal to the change in meters over seconds. So I would write that in IB, we need to write it in this form, okay? I never write it in a fractional form. Okay, that's so we don't get confused. So meters per second is written in that form as shown in your text. All right, now because it's a combination of fundamental units, we would say that this is a derived. Okay, so just to repeat, important that meters per second is symbolized as ms to the -1, which puts the s down there. That is how we need to write all our units in IB physics from now on. Show that force is a derived unit. Well, from last year we knew that F is equal to ma, or fm, okay? And m, mass, is always measured in kilograms, so I'm just going to write this out. Kilograms. And acceleration is the rate of change. It's the rate of change of my velocity over time, which is equal to meters per second over second. You see how I'm writing this? This is why we don't do this. It's so confusing. So instead of writing it that way, I should always be writing it that way, okay, which is informing me that the S has to go down to the bottom. So really what that means is m over S times S, which is equal to m over S squared, which if I want to write that is ms to the -2, okay? So acceleration is meters per second squared. And then when I multiply those units together, kilograms times meters per second squared, I get kilograms meters per second squared. Okay, that's a derived unit because it's a combination of multiple units, kilograms meters per second squared. And again, notice how I've written the exponent here. It's not left in that fractional form. Now, last thing that we're going to do in this video is we're going to show that work is a derived unit. So how do I show that work is a derived unit? Well, work is equal to, do you remember from last year? Work is equal to mad. I know we talked a lot about that. Or work is equal to force times distance. That's how we got to work is equal to mad. So work is equal to force. We just talked about what the units for force is. Okay, force is kilogram meter per second squared times the distance, okay, which is measured in meters, gives me kilograms meters squared per second squared. Whoa, that's wild, okay? And that's a derived unit as well. Okay, so that was an explanation of derived units. Now, you can stop the video here to take a break, but you know what? I'm just going to keep it going. And the next section that we talked about in our lessons today are orders of magnitude and measurement. Okay, you had a little quiz about that. So as physicists, we are very good at estimating the size of stuff in the universe, or we think. Okay, as you've seen, this is from a movie called The Princess's Bride. It's one of my favorite movies with rodents of unnatural size. Okay, so we categorize size in terms of orders of magnitude. All right, and we did a little bit of that practice. Instead of saying something is about 1.2 meters or 5.8 meters, we would say what range in meters it is. And the classification of range is based on the scientific notation. So I would say that the radius of the universe is 10 to the power of 26 meters. It's in that ballpark, okay? And the human being, which I'm about 1.7 meters, okay, my range is going to be 10 to the power of 0. 10 to the power of 0 is on the order of single-digit meters, okay? So these are all orders of magnitude that we practiced today and that you've seen in your textbook. And a good question came out today in class saying, do I need to know these? Yes, you have to have a relative understanding of the range. You need to know these identical. You'll have questions about that on the exam. You need to know these as well, the relative sizes and masses of things. Some of this you can find in your IB data booklet, which I'll present later on. Okay, so let's do some work with it. How many orders of magnitude larger is the radius of an atom compared to the radius of a neutron? So if I go back to this table, the radius of an atom is 10 to the minus 10, and the radius of a neutron is 10 to the minus 15. So if I want to look at that ratio, I would say an atom to the neutron, you got 10 to the minus 10 meters divided by 10 to the minus 15 meters is going to give me 10 to the 5. Okay, that's how many orders of magnitude larger the radius of the atom is compared to the neutron. Okay, estimate the relative order of magnitude for a human heartbeat per minute while resting. So mine is about 73 beats per second. Okay, oh no, beats per second. Wow, I would be flying. Okay, beats per minute. Okay, so what would be the order of magnitude? 10 to the power of 0 is like 1 to 9. So it's much greater than that. 10 to the power of 1 is now 10 to 99. 10 to the power of 2 would be like 100 to 999. So I'm below that, I'm above that. Okay, the order of magnitude would be 10 to the power of 1. Okay, the average human lifespan in North America is 81 years. Okay, seems like a little. I want to make that a lot more. Okay, for women, it's 76. For women is 81. Okay, you're luckier. You get to live 5 years longer than us boys, which is 76 years. What is the order of magnitude for a human lifespan in SI units? See, I want to feel like I'm going to live longer. So if I convert that into SI units, it might help me out. So how would I convert, let's say, 81 years into SI units? Okay, so one year is equal to 365 days. It's a little bit more than that, but let's just round it to that. Okay, and then 1 day is equal to 24 hours. Okay, 1 hour is equal to 60 minutes. And 60 minutes, and 1 minute is equal to 60 seconds. Okay, so if I want to convert, everything in the end has to be seconds. So I have to use all these proportions to be able to get that answer. So pause it, try to do it on your own, and then come back. Well, if we're going to do that, I would then have to set this very long conversion up. 81 years times 365 days per year times 24 hours per day times 60 minutes per hour times 60 seconds per minute. Okay, now I'm just checking things out. The years are going to cancel. My days are going to cancel. My hours are going to cancel. My minutes are going to cancel, which leaves me with seconds as the unit. So if I multiply all these numbers together, okay, I should get to the answer. And the answer is going to be, let's see if I still have it in my calculator. It's like 2 point something times 10 to the power of 9. So then I would say it's about 2 times 10 to the power of 9, which means that the order of magnitude is 10 to the 9 seconds. Okay, and if I did the same calculation for the men, which is a little bit smaller, it still ends up 2 times 10 to the 9. So both men and women have an order of magnitude of 10 to the 9 seconds for your life. So make every second count. You only have 1 billion of them.